try and return things to normal. Is now is the screen. Should be sound. Not sure. Okay. What?
The start menu, remember? Remember it was on the start menu?
Ah, yeah. I'm not sure which start menu, but yeah. Found it. Yeah. Okay. So I'll go back to the shader, to the kernel, and turn things to normal. Run it again, and you can see that the flags are getting back to normal. We have lots of other tons of debugging features. One of them is the memory viewer. So this gives a unified view of both the GL and CL memory usage. You can see that the CL context, the amount of memory is used for images, for buffers, for command queues, and these are the GL context and the amount of memory they use. And you can also ask GDebug to break on memory leaks. So whenever there is a GL or CL memory leak, it will break and will display the call stack that led to the object creation. Switch over to a short profiling demo. For this, I'm loading a demo that I think for the OpenCL programming guidebook. It's coming soon.
Yes, it's an Ocean demo, so it's just doing a simulation of an FFT with generating line maps and so on. It's going to register in GL.
That's a very nice Ocean demo. You can see the waves and the reflection and everything. So I switch to profile mode, and where GDebugger removes all of the heavy logging operations, so you can profile. And we have few profiling methods. One is this view, which gives you an overview online on what's going on in CL. So you can see that 4.3% is of the time is spent in kernels, and there are some synchronization issues. And you can see also how many work items per second. There's 42 million, and how many read and copy megabytes per second are there. This is a nice overview. If you want to go deeper, we have another view. This is the commands queue viewer, and it's like a GAN. So you can see a GAN of the OpenCL activities. And here you can see, a typical batch, which all the commands are doing. And so you can see that there is a batch, and then there is nothing happening in the OpenCL, and there's another batch, and nothing happening, and then there is another batch. And for each enqueue command, you can see its properties. And this is a very nice drill down that lets you optimize your application. We also have performance counters from different suppliers. We have our own performance counters, which are per queue, that count all kinds of things, like how many computational frames per second, what is the utilization of kernel commands, write operations, and things like that. We have integration with the API Stream SDK, which gives a very nice set of performance counters. And we have, of course, the operating system counters, and also OpenGL counters, and so on. So you can also locate performance bottlenecks using counters, like you can display them as bars or SIGGRAPH. This was a very short introduction to GDebugger. Overall, we found that GDebugger helps users to improve their application quality and shorten their debugging time, and we get very nice feedback about this tool.
So hello everybody. My name is Ofer Rosenberg, as you can see from Intel. I belong to the Vision Computing software division, and we're going to talk today about optimizing OpenCL CPUs. So first of all, a small recap to what Yaki said. Yaki mentioned it, and I want to repeat that. That OpenCL is what we call a platform API. So basically, it supports a uniform programming environment across devices. The goal of OpenCL, using it, should be to make the best use of all available resources, which are the CPU and the GPU, within a single program. That's the basic idea of OpenCL, that you're probably using all of your devices back together inside one program, and one programming model. And we want to mention that Intel is coming up with a new generation of processors, which we call the new generation. We call the graphics there, we call them processor graphics, because they bring a new level of integration between CPUs and GPUs. This is already coming from, starting from Sandy Bridge. So what's the challenge today of actually using multi-core CPUs? How many of you are programming CPUs today, trying to utilize multi-cores and vector units? So it's a problematic issue to try and unleash the power of the CPU, because you have to exploit the multi-core, and then you have to exploit the fact that you have SSE registers, which are not easily accessible. So OpenCL is a great framework to harness this power within the CPU. First of all, it's very intuitive, as Afi explained to you. To write a program in OpenCL, it spans across your device. And it unleashes the performance of CPU by using multi-cores and utilizing your vector units without the need to write special code which targets the vector units. And, as I'm going to show you, actually the results can become very close to hand-tuned code. Okay? So you keep within your C language. Okay, you're using some vector types, you may manipulate your code a little bit, but it's still C language. You're getting very close to your hand-tuned SSE. More important than that, we're talking about a performance portable code. We're talking about forward compatibility between CPU generations. When the CPU comes with a new ISA, if your code comes in OpenCL, it automatically compiles for the new ISA. For example, we're going to have AVX, the code compiles to AVX. And there will be the next ISA, the code will be able to compile to that. So this is what we call forward compatibility. In addition, we aspire to have compatibility between devices. Okay, it's aspiring because you need to keep in mind that OpenCL is a rather new thing. We have implementations in the market that need to become more mature to enable actually this compatibility between devices. So let's have a view of how OpenCL is actually mapping out Core i7. So this is part of the spec. This comes from OpenCL platform model, as Afi showed you. And this is our Core i7 975. Well, if you look at it, it has 8 compute units, because it's a quad-core, and it has SMT inside, which means that it has 8 logical cores. And the number of processing elements that the CPU exposes varies, because we have a 128-bit SSE register. So it depends on your computation type. If you're using floats, it means that you have 4 elements. If you're using chars, you have 16 elements. And we know how to use that, by the way. So, in addition, we have a cache hierarchy inside our CPU. It doesn't appear, it's not part of the programming model in OpenCL, but I'm going to touch it briefly and show you actually how using the caches that we have inside the CPU is actually helping you to move from C to OpenCL in a much lighter and easier way. So we talked about it in the past in the other box, and I want to mention again that there are probably 2 styles to write OpenCL code. Implicit and explicit data parallelism. The implicit one is what every graphics developer knows as shader programming. You write your kernel as what we call a scalar program, which means that you're using vector types which size naturally to your problem. If your problem is a pixel which has 4 elements, then you're using float 4, not because of the fact that we have a register which is 4-way floats wide, but because float 4 is your problem basic data type. And it maps automatically to single compute resources by the compiler and the runtime and the hardware. The developer is not trying to match the actual machine architecture. This is what we refer as implicit data parallelism. Explicit, on the other hand, is where the kernel is defining one stream of instruction targeting the compute unit, which in the case of the CPU is the logical core. There you get parallelism for a source level wide vector types. The developer is writing the vector types because he wants to target the actual hardware. And there it's important to size the vector types to match the native hardware width. We have a new query in 1.1 which enables you to know what's the native vector width of the machine. And the programmer hints the implementation to know that he's writing it in explicit mode. This is the pragma, which is called the vector hint type, where the compiler sees that and he knows that it doesn't want to vectorize the code. CPU supports both mapping. It's a matter of software, the right software to write, to know how to exploit each one of them. I'm going to focus in this presentation on the first one. I'm going to show you actually how shader-like or implicit data parallelism maps on the CPU. Let's start with a little example. Okay. So n-body simulation, anybody is not familiar with n-body, haven't written n-body or anything. N-body is probably the most widely used example in the world. The idea is that you have particles, and each particle is affecting the other particles. Each particle is affected by gravity forces, and it affects its position and its acceleration. Basically, it's highly parallelized because each particle can be calculated regardless of the others. So each step, you actually need to go through all of the particles in the system, and for each one of them to calculate the influence of the rest of these particles on this specific one. And this is actually what you see here. This is an n-body function, okay? You have an outer loop, which goes on all of the particles, and inside you have an inner loop, which calculates the influence of all of the bodies on this specific body that you're calculating right now, and then you're updating the position and the velocity. As simple as that. This is a C program, okay? As I mentioned earlier, one of the problems when you go and write this code, it doesn't span across your cores unless you explicitly do that. And it doesn't utilize your vector units unless you write it in SSE or in OpenMP and any other methods. Okay. Now let's see how to convert it to OpenCL. So first of all, we need to replace the headers. Okay. It's a very slight and delicate change. Okay. We had buffers. We're keeping the buffers, but now we're just adding the global before them because they come from the global address space. And if you recall, I'm writing my kernel for one point in my data range. So this outer loop here, I don't need it anymore. It's replaced by getting the index. And this is the kernel. This is the change. I have a kernel specifying one body, and this is the entire change. And as I mentioned earlier, the fact that we have caches, actually I'm not using local memory here at all, because on the CPU, you're not required to use local memory.